Hello everyone, my name is Makanga Christopher, and today we are going to be reviewing a paper called Adaptive Graph Learning Method for Automated Molecular Interactions and Properties Prediction. The paper was authored by the following people, and let's get right started. Now, when we look at this paper, the authors were trying to mitigate or to fight to tackle a problem which is estimating molecular interactions and properties, and also trying to improve drug discovery efficiency. Now, this they were doing by searching for potential drug candidates from a vast majority of chemicals by using low cost and high speed methods of discovery. So that's a problem. And the computational problem they were trying to identify was developing a flexible, they were trying to tackle was developing a flexible and reliable graph learning method that can adapt to any given data set and make accurate predictions of molecular interactions and properties without human intervention. Now, they proposed a solution of graph learning based on adaptive machine, graph learning based adaptive machine. As we know, as we have seen that we are trying to tackle reliability, flexibility, and adaptivity to data sets. So they propose this method because it can tackle all those problems that we have looked at. And they are also trying to compare this with the previously used methods and to investigate its robustness and interpretability as opposed to the various methods that were used prior to this. Yes, so the next thing we are going to have an overview of the method. Now, unlike other methods that have been used for graph learning, and the authors identified GLAM, which is graph learning adaptive machine, as a method that does not require human intervention. It uses an automated pipeline to learn from the datasets and to build a predicator, whereas the other methods require a human, as we can see in this diagram, that once data is fed into the once data is fed into the okay, once its data is fed into the configurations, GLAM samples the configurations, then data is fed into these configurations, and GLAM performs a low fidelity training on the data. After performing a low fidelity training from the data, they select high performing configurations, and after selecting those high performing configurations, it's GLAM. All this is happening automatically in our automated pipeline. Then it undertakes a high fidelity training. Now, after undertaking a high fidelity training, it releases predicators. Now, these predicators are evaluated, and the best predicators are blended to create a predicator. Now, whereas with the human procedure, what happens is a human expert is required to design the architecture, to set the hyperparameters, to select the loss function, to select the criterion, to train the model, to evaluate and create the predicator. So this whole process that has been done by a human expert is being replaced in the GLAM by our automated pipeline. Now, in greater detail, how the automated pipeline works. So we have our GLAM samples configurations from a given set of configurations. It initializes by sampling the configurations. Then now the sampled configurations are fed with data sets. Now, when they are fed with data sets, GLAM performs low fidelity trainings When it performs a low fidelity training, as we can see here, it uses few epochs to perform low fidelity training. And then these are evaluated based on their score. It outputs scores, and then the configurations are evaluated based on their scores. And those that have performed well are then the best configurations are taken for high fidelity training. And when they are taken under high fidelity training, it uses full epochs and it produces what they call this. It produces the scores. These scores and predicators. So it produces predicators and their scores. Now the predicators are evaluated, and after they've been evaluated, the best performance predicators are blended together to output one blended predicator, as we can see in our diagram. Now, from there, the authors designed two architectures they designed two architectures for molecular interaction and properties prediction. This is the architecture for molecular interaction, and this is the one for properties prediction. Now, what happens in these architectures is first there is a pre-processing of a molecule to a molecular graph. It's what happens here, what is shown here. And then this molecular graph, it is linearly transformed by the feed forward block. After it is transformed by the feed forward block, it is iterated. It is iterated convolutionarily by message passing block, as you see the iteration here, and it's also here from message passing block, fusion block, and then message passing block, fusion block. So that iteration, it's called convolutionarily. And then this happens for t times steps. It happens for, as we see it identified here. Then it's then taken for node reduction by the global pooling block. Once the nodes are reduced, it is linearly transformed once again by the feed forward block, and then that's how that's our architecture for molecular interaction, this and properties prediction. Now, before we go any further, let's look at our data sets. Now, since GLAM is designed to adapt to any given data sets, the authors chose to investigate its adaptability and performance by using 14 data sets with a range of traditional methods, and these data sets included protein interactions, drug to protein interactions, drug to drug interactions, physical to chemistry property, bioactivity, pharmacokinetics, and toxicity. So the data availability, all data that is used, that was used by the authors, can be accessed as follows, as you can see here. Yeah, if you're interested, you can check it out. Now, the performance of GLAM as compared to other models for different data sets, as you're going to see here. So we are trying to check out the performance comparison on data sets of molecular interactions. Now, what happens here is that we have GLIDE. We have GLIDE, GLIDE SP and GLIDE XP, and then we also have now we also have RF score and DGraph DTA, then transformer CPI and GLAM. So we are comparing them on these data sets, and as you can see from each data set, GLAM was performing better than all the rest of the data sets. And actually, these data sets were adjusted to get the best performance from them. So that's why you see the parameters on adjustment. Yeah, so from the performance comparison on data sets of molecular interactions, we can identify that GLAM performed better than all these other metrics for its comparison. As we can see that GLIDE docking scores were obtained on Schrodinger version with a precision of SP and XP, then RF score, which is a random forest based scoring function for virtual screening, and then so this dgraph DTA and transformer CPI were implemented from their open source code. Now, performance comparison on data sets of molecular properties. We have metrics as GCN graph convolution networks, GTA, GNI, MPNN, alternative FP, MolMapNet, and GLAM. So what we are trying to do here is we are trying to compare GLAM with these other models or metrics and on these data sets. And of course, we looked at the physical chemistry. These are the data sets used. Bioactivity, these are the data sets used. Pharmacokinetics, these are the data sets used. And toxicity, these are the data sets used. As I said, the parameters were adjusted for better performance. And as we can see, when we try to look through the performances of the different data sets, on average, GLAM performed better than all the other identified data sets. Sorry, all the other identified metrics on our data sets that we selected for evaluation. And these are the results as this. We try to compare GLAM with our traditional methods, graph learning methods, and as we have seen in tables 1 and 2. And then we came out to identify that GLAM achieved or performed on an average of 18.7% decrease in prediction error on all the 14 data sets compared to the best of the traditional methods that we have been looking at. And GLAM consistently achieved the best results without human intervention, whereas the other methods required human intervention. Therefore, the authors concluded that GLAM is flexible, reliable, and trustworthy, and it can work well across a wide range of activities in drug design, and it can perform well across a number of data sets. Whether the data set is small or the data set is big, GLAM will always be your best choice. Now, when the next thing is high robustness against molecular structure, perturbation. Now, what happens is all methods undergo perturbation when faced with different molecules. So the output is always affected when for different methods, as they are faced with perturbed molecules. So what the authors did, they fed the original molecules and perturbed molecules to the predicators that were created by the different modules and investigated the differences in outputs. And as we can see in this table, they were investigated on different they were investigated on different predicators for the different methods. As the table shows, GLAM performed better than all the other methods, all the traditional methods, and the authors concluded that the robustness of GLAM is most probably due to the model blending and at the end of the pipeline. This blending were the best predicators are blended together to form one predicator. That's where GLAM outshines the other methods. The other methods. Now, ablation studies, time consumption and resource costs. GLAM costs 10 times more in terms of time, consumption, and 4 times more in terms of resources. But the authors, however, they concluded saying that it is necessary that GLAM should be costly as compared to the other traditional methods, because GLAM has a better performance than the other methods. And then preferences analysis. GLAM may lead to ideas. The preferences of GLAM may lead to ideas for the design of new methods. And as we have analyzed, we have seen there is that GLAM is preferences analysis was performed on 3 sub-representative datasets: ESOL, BBP, and TOX21, and and prefers the global pool method of an analysis. And from the configuration, the analysis of preferences of GLAM in multiple configuration items, as shown in the supplementary table 3, shows that GLAM offers more room for more methods to be developed on top of it. And this is what I was talking about. Yes, this. So it was tested on 3 data sets, and GLAM proved to be to have more room for development of other ensemble size. So we can also, the authors concluded that performance is improved as the ensemble size is increased from 1 to 3 and remains stable from 3 to 7, as shown here. But ensemble size is when we go back here, ensemble size is actually what determines the predicators to be chosen here and to be blended to come up with this one predicator. So okay, so the configuration space of GLAM has 2 parts. It has the architecture decisions and training decisions. The architecture decisions decide how to build the architecture of the model. The general architectures of pairs of molecules and single molecules contain 8 and 4 blocks with their own independent design spaces respectively. And then the training decisions decide on how to train the model, for example, batch size, the number of the epochs, the type of loss, type of optimizer, learning rate, among other things. And then limitations and frontiers. The adaptive feature input can help models in our proposed method to extract important sufficient representations. So as GLAM increases or decreases, as it adapts to different sizes of data sets, this can help our model to extract important and sufficient representations. So since it adapts to any size of the data set, it can easily choose or extract the most important features that we may need to perform our training. And then the GLAM, the authors describe the graph model with basic node features such as atomic residual, atomic/residual number. And then the adaptive feature input can be of great help in some particular prediction jobs. Adapting feature decisions to the configuration space might improve the author's proposed method. So as I've talked about it, that how it adapts to different data sets, it may improve or adding more features to a data set may improve the configuration space, which in turn improves the GLAM method. Yeah, so strengths and weaknesses. As we've said, GLAM can adapt to any size of any data set without human intervention. And then GLAM is robust against molecular structures, structure perturbations, meaning the output is lessly affected as more perturbed molecules or original molecules are being fed into the predicator. And then GLAM can provide meaningful interpretability by visualizing the hidden state of the models, revealing the important atomic groups and interactions for the prediction task. And GLAM can facilitate automated drug design by serving as a reliable predicator generator that can leverage graph learning to search potential drug candidates with fast and low cost. Yeah, so as as the authors said in the beginning, that they were looking for something that is fast and low cost, and that can be reliable and flexible. So because of its adaptability to different data sets and its performance without human intervention, that makes it a very good method for predicting for drug efficiency or for identifying potential drug candidates. And then the limitations, the adaptive feature input can help models in the proposed method to extract important. Oh, sorry. The weaknesses of GLAM. GLAM is computationally expensive, as we saw that it's 10 times more in terms of time and 4 times more in terms of resources compared to the conventional methods. And GLAM relies on basic node features such as atomic number or residual number, which limits its ability to capture more complex and diverse molecular information. And GLAM uses a random search strategy to sample configurations, which is not very efficient. You get? Since more efficient configurations might be skipped, so it is not an intelligent way to optimize a model truly. And in conclusion, GLAM performed better in terms of prediction performance on the 14 data sets, and its adaptability is commended, and its performance without human intervention is really commended. And and because of this, it's really reliable, trustworthy, it's robust, and it can be easily interpreted. So if the author can, if there is a way of making it computationally cheaper, then GLAM is really the best method for drug prediction. And finally, these are my citations. Thank you very much. Have a nice time. If you have any questions, you can leave them in the comment section.